When you look up at the sun, what do you really see? I mean, sure, it's a giant ball of fire, but it is so much more than that. It's a cosmic engine, and it's powered by this incredible process called nuclear fusion, something scientists have been trying to recreate right here on Earth for decades. So today, we're going to dive into the physics behind this amazing power source and our quest to, well, build our very own star.
I mean, building a star on Earth? That is a wild statement, isn't it? But honestly, it just perfectly captures the sheer ambition of this whole thing. We're not just talking about a new way to get electricity. No way. We're talking about tapping into the fundamental power of the universe itself. It's this massive challenge that's had scientists hooked for nearly 100 years. So yeah, let's get into it.
Okay, so to really get what we're trying to build, we first have to look at the original blueprint, the sun. Deep inside its core, the gravity is just so intense, it creates what's basically a pressure cooker on a cosmic scale. And that is where the magic happens. It's where matter gets converted directly into the energy that warms our planet and, makes all life possible.
So what is actually going on in there? Well, at its most basic level, nuclear fusion is all about taking really light atoms, think hydrogen, and just squeezing them together so incredibly hard that they fuse into a single, heavier atom, like helium. And when that happens, a tiny little bit of their mass disappears and is converted into a huge amount of energy. Yep, that's Einstein's famous E=mc² in action. Sounds simple enough, right? So why aren't we doing this everywhere?
Well, that's because there's a pretty big catch. You could almost think of it like an invisible force field that stops fusion from just happening all over the place. It's this fundamental barrier that's built into the very heart of matter.
Okay, think about this. You ever try to push the same ends of two magnets together? They just refuse to touch, right? They push each other apart. Well, it's the exact same idea with atomic nuclei. They're all positively charged, so they naturally repel each other. This repulsive force is called the Coulomb barrier, and it's the #1 reason why fusion is so incredibly hard to do.
So what you have is this constant tug-of-war between two of nature's fundamental forces. On one side, you've got that electrostatic force, doing everything it can to push those nuclei apart. But on the other side, you've got something called the strong nuclear force. And this one, well, it's way more powerful, but it has a catch. It only works over incredibly short distances. The trick is, if you can somehow shove those nuclei close enough together to overcome their repulsion, that strong force takes over, snaps them together, and that is when you get that massive release of energy. Okay, so how in the world do we get those nuclei close enough to actually fuse? I mean, we can't exactly build a machine that has the gravity of the sun, but we can do the next best thing. We can turn up the heat. And I mean, turn it up a lot.
We're talking about temperatures over 100 million degrees Celsius. Just to put that in perspective, that is more than 6 times hotter than the core of the actual sun. It's just insane. And at these kinds of temperatures, something pretty amazing starts to happen to the fuel. The fuel transforms into what's known as plasma, the fourth state of matter. Basically, it gets so hot that the electrons get completely stripped away from their atoms. What you're left with is this superheated, chaotic storm of charged particles. And in this incredibly energized state, the nuclei are just zipping around so fast that they can finally slam into each other and overcome that repulsion to fuse. Right, but it's not just about using any old hydrogen. Turns out, for a fusion reactor here on Earth, we need a very specific blend of ingredients, a special recipe, if you will, to get the most bang for our buck. And that perfect fuel mix seems to be 2 heavy versions of hydrogen called deuterium and tritium, or DT for short. Deuterium, well, that's pretty easy to find. It's in seawater, so we've got tons of it. Tritium is a little trickier, but the cool thing is we can actually create it inside the reactor itself. And the reason this DT mix is so great is that it fuses at a lower temperature compared to other options, which makes it the go-to fuel for the first generation of fusion power plants. So what happens when a deuterium and a tritium nucleus finally slam into each other? You get a big release of energy. They combine to form a harmless helium nucleus and one spare, super high-energy neutron. And it's these 2 resulting particles that fly off carrying all that newfound energy. And when I say a massive release of energy, I really mean it. Pound for pound, this fusion reaction releases over 4 times more energy than nuclear fission, the process we use in today's nuclear power plants. But here's the real kicker.
Unlike fission, this DT fusion process doesn't create any long-lived, nasty radioactive waste. And that right there, that's an absolute game changer. Okay, so we've got our fuel. We know we have to get it incredibly hot. But this leads to a brand new, very practical problem. How on earth do you contain something that's hotter than the sun? I mean, seriously, if that plasma touches anything, it would just instantly vaporize it.
To pull this off, to actually achieve sustainable fusion, physicists have to master 3 critical conditions all at the same time. It's called the triple product. First, you need that extreme temperature. Second, you need to pack the fuel in densely enough. And third, and this is a big one, you need to hold it all together for long enough to give the reactions time to happen. And the solution they've come up with is just brilliant. It's a magnetic bottle. In amazing machines called tokamaks, scientists use incredibly powerful magnetic fields to create an invisible cage. This cage traps the super-hot plasma, suspending it in midair so it never, ever touches the reactor walls. It is, quite literally, a star in a jar. Now, the ultimate goal, the holy grail of all fusion research, is something called ignition. This is the magic moment when the fusion reactions themselves start producing enough heat to keep the whole process going. It becomes self-sustaining. You can basically turn off the external heaters and just let your little star burn all by itself.
So after all that, why are we going through all this incredible trouble? What's the big payoff at the end of the day? Well, because fusion power really is the ultimate prize in the world of clean energy. Think about it. It's completely emissions-free. The fuel is just about limitless, and it's incredibly safe. There's no physical possibility of a meltdown or a runaway reaction. And like we said, no long-term radioactive waste. On top of all that, it provides firm 24/7 power, making it the perfect partner for renewables like solar and wind. And getting electricity out of this whole process, it's actually the most conventional part. All that incredible heat from the fusion reaction is used for one simple thing: to boil water. Seriously. That creates steam, the steam spins a turbine, and the turbine generates electricity. It's pretty much the same way we've been making power for over 100 years, just with a revolutionary, clean, and ridiculously powerful new way to make the heat. Look, the journey to get to fusion power has been a really long and challenging one. There's no doubt about it. But with all the incredible breakthroughs we're seeing in science and engineering lately, we are closer than we have ever been to finally unlocking the power of the stars. It really feels like the question is shifting from if we can do it to just when. So are we standing on the edge of a new age of clean, limitless energy? The future of fusion has never, ever looked brighter.